Hello DSP friends. Today we're going to talk about the Parks-McClellan method for designing Finite Impulse Response or FIR filters. These are the topics we're going to talk about. We're going to talk about how to use the Parks-McClellan method to design FIR filters, an overview of how it works, a comparison with other FIR filter design methods, and finally we'll go through some design examples. So, what is the Parks-McClellan method? It's the most popular technique for designing finite impulse response filters, and it's also called the Equiripple, Chebyshev, or Ramey algorithms. Those are kind of interchangeable. MATLAB uses the term Ramey or Ramez, however you pronounce it. The algorithm was published in 1972 by James McClellan and Thomas Parks in Fortran, and has since been ported to lots of other languages. It's widely used for designing FIR filters, kind of the gold standard for that purpose in digital signal processing. So why is the Parks-McClellan algorithm so widely used and so popular? Its input parameters correspond to the normal digital filter design specifications that you create in creating an overall DSP system. It creates the optimal design for those parameters, and it's also quite flexible. It can design lots of different categories of FIR filters. The most obvious ones are the simple low-pass, high-pass, bandpass, and bandstop filters. It can also design multi-band filters, that is, filters that have multiple pass bands or stop bands. And it can design Hilbert transforms that are useful for creating complex signals. You can also design differentiators, although that's not a commonly used application anymore. So, given all the good things I've just said about the Parks-McClellan algorithm, why would you use a different design method? And there are a variety of other design methods. Really, for general use applications, the Parks-McClellan is preferred, but there are some specialized applications that it might not be. One of the disadvantages of it is it's an inherently iterative design method that isn't guaranteed to converge, and it's not suited to designing filters on the fly, in some sort of live real-time application. Like an example would be an audio equalizer. There are also some methods that result in a simpler implementation. For example, there's a type of filter called boxcar filter where all the coefficients are the same value. And that's useful in some applications. Another thing would be if the filter design has specifications that don't fit the Equiripple model. An example of that is a notch filter, where you might want the notch frequency to be as attenuated as possible, essentially 0, rather than some specified number of dB of attenuation, which is what the Parks-McClellan algorithm would accept as a parameter. So how does the Parks-McClellan method work? It's rather complicated to explain in detail. Wikipedia provides an explanation of that, as well as most advanced DSP textbooks also provide an explanation. I'm not going to go into a lot of detail on that here because for most practical purposes you really don't need to know how it works. You really need to know how to use it. But some key points to think about is it's making a guess in the frequency domain about the contents of each pass band and stop band. It does an iteration to evaluate the errors that result from the guess. It improves the guess using something called the Ramez exchange algorithm. And that's why this method is sometimes called the Ramez method, kind of incorrectly. That's a subset of the overall algorithm, but it's kind of the heart of it. And MATLAB uses that term, so just be aware that when they're saying Ramez, they aren't giving enough credit to Parks and McClellan. But it goes back and forth, iterates, makes an improvement, and since this is an iteration, there can be two things that can happen. It can converge upon a solution, or it can fail to converge and that gives you the situation where the design has not been successful. Generally speaking, the algorithm can converge on any design that has realistic parameters up to some limits. There are limits in the numerical precision that the computer uses, which is a limit for very large filters in the thousands of taps range. You won't run into that with most normal filters. The other problem can occur if you have too few taps specified, or even too many taps specified way beyond the range of what the design calls for. So those are things to kind of bear in mind as you use this. Next, let's introduce some filter terminology. Every digital signal processing system and filter has a sampling frequency, which is usually called fs. That's also sometimes called sampling rate. Those are interchangeable terms. We have some basic filter response types: low pass, high pass, band pass, and band stop. Another Parks-McClellan term, passband ripple. That's essentially how much the response varies across the passband. You'd like it to be ideally flat, but it never can be. So that's another design parameter. How much ripple is the filter design allowed to have across the passband? Stop band attenuation is the next one. How much do we want the stop band to be stopped? That is, eliminated. Ideally that would be completely eliminated, but again we have to make some realistic compromises. That's usually specified in decibels or dB, as is the passband ripple. And essentially more attenuation is better, but also results in a more complex filter design, so there's a compromise to be made there. Number of taps is a feature of every FIR filter design. Taps, if you're not familiar with it, amounts to the number of coefficients that a filter has, fundamentally, usually the same as the number of memory elements, although that isn't always the case. In simplest terms, that amounts to how much computation does the filter require for each input sample, and also how much memory is involved. So basically, the fewer taps the better. And in FIR filter design, we typically want to have the minimum number of taps that meets the required specifications. And that's kind of where the optimal part of Parks-McClellan comes in. We want to have an optimal design in the sense of meeting specifications with the minimum number of taps. Next, let's compare the Parks-McClellan algorithm to other FIR filter design methods. The thing that ties all these methods together compared to the Parks-McClellan algorithm is that they all can be done in a closed form basis, basically with a formula. So there's no iteration involved. Boxcar type is sometimes called moving average, is simply the average of the last n number of samples. So in finance, for example, they often use a 15-day moving average, meaning that the output is the average of the last 15 samples of, let's say, the stock price. Well, we can also do that in DSP terms. That's usually called a boxcar filter. And the key point there is the only parameter we have to work with really is the number of taps. So the larger the number of taps, the longer the average will be. It acts as a low-pass filter, essentially, and you have less noise in your signal as a result of the longer you average. Next, we have the windowing method, which can also be extended to something called windowed sync, and that has the advantage of you can work on a formula basis using the well-known data windows that are often used in spectrum applications or FFT, DFT applications. The parameters there are the choice of window, type, and the number of taps again. Next we've got raised cosine and root raised cosine, which are used in some specialized data modulation and demodulation applications. We won't go into those here, but they do have this common feature of operating from a formula and some parameters. You can design the filter directly. Another type is called maximally flat, which has a, as the name suggests, a maximally flat passband. And that's in contrast to the Parks-McClellan design, where we're giving our passband some sort of ripple allowance, and we allow the passband to deviate between a positive and negative side of a ripple relative to a desired passband response. The maximally flat type has the advantage of flatness in the stop band over a Parks-McClellan method, but it has the disadvantage that you don't get to specify what goes on in the stop band independently. So the stop band is kind of tied to the other specifications that you're trying to use around the passband. And for most applications, you really don't need this kind of extreme maximal flatness. And if you think about Parks-McClellan design parameters, you can set that passband ripple to be arbitrarily low to whatever dB you want to, if you've got enough filter taps to support that. So a maximally flat type is maybe of interest for some specialized applications, but really it's not something you would use very often compared to a Parks-McClellan design with just a very small ripple in the passband. I'm going to be going through our Parks-McClellan design examples using Scopefur, which is a program I wrote many years ago that is specialized for that purpose. What you see here is a low-pass filter design, 1 kHz sampling frequency, 0.1 kHz passband upper frequency, which corresponds to this point, 0.2 kHz stop band lower frequency, which corresponds to this point. Since this is a low-pass filter, the stop band upper frequency is always half the sampling rate of 500 Hertz in this case. So this illustrates a few basic points of Parks-McClellan design. We've got a passband ripple allowance of 1 dB from this specification. That turns into plus and minus half a dB around a nominal magnitude of 0 dB, or linear gain of 1. We've chosen a stop band attenuation of 80 dB, so that shows on the graph as minus 80 since it's attenuation. You'll notice that these peaks in the stop band all are less than 80 dB, so this was a successful result. We've got, I'll zoom back out, we've got some areas that go extremely low. These are zeros of the filter, if you're familiar with the concept of zeros in a FIR filter. But basically these are frequencies in which the response of the filter is exactly 0. And I covered these things in another video that I'll provide a link for. So if we experiment with some of these parameters, which I've done in more detail in the other video, I'll just put in 60 dB for the stop band attenuation. We'll optimize that, and Scopefur automatically figures out it needs 23 minimum taps to realize that filter, and that was successful. Now if I put in some other number of taps, like I'll put in 20, just a little bit less, and design, the design is successful in the sense that it converged on something, but it's unsuccessful because it didn't meet the specifications. And that's a case where the filter has been starved of the number of taps it needs. So there's really nothing that any FIR filter design process can do about that. Now if we go to a higher number than the 23 that we know works, let's go to 30. That also works, but you can see that we've got more attenuation than we needed in the stop band, which is okay, but we had too many taps. Now I'm going to go crazy and put in 300 taps, and we'll see it may fail at that, or it may succeed. Okay, so the message here is the Parks-McClellan design algorithm failed to converge. And it offers some suggestions. So since this is 10 times as many taps as the filter requires, it won't be successful with that many at all. So I'll put in 60, which is a little over twice what was required of 23. That works. You can see we get lots of attenuation down here in the stop band. Double that again, 120. That also works. 240. So it fails to converge. So that's kind of one of the lessons here, is that the giving it way too many taps is causes a lack of convergence in the Parks-McClellan design algorithm. From experience, you would kind of know to use fewer maybe as something to try. Scopefur also has an estimation capability where it estimates what the number of taps is. It estimated 22, and the estimation, as per the name, is not perfect. So you can see that the design converged, but it didn't quite meet our specifications. But the estimate gets us fairly close. So there's a range where the algorithm will converge, but it might not quite meet the specification if it's too few taps, or if it's grossly too many taps, it'll fail. But if it's slightly more than the number of taps that are required, it will generally succeed, but you'll get a design that is more than you really need. And there are some reasons why you might want that in some cases. Like, let's say, for reasons I won't go into here, let's say I need the number of taps to be a multiple of 5. Well, I can try 40. That works. It gives me more than I need. Since 23 worked, I can be pretty sure that 25 will work. That also works. So a little bit more taps than you really need is fine. That's where this estimation capability is helpful to get you in the ballpark. And with the Scopefur's optimize feature, that allows you to basically, it does a trial and error process that determines what's the minimum number of taps that will work for your specifications. So next I'm going to do an analogous design that's a high-pass filter, uses all of the exact same specifications except for the band edges between stop band and pass band are interchanged. And as I hit this high-pass button, you'll see that these automatically get updated to kind of reuse our parameters for a high-pass situation. And I go into that in the other video in more detail, but basically, since all the parameters were the same in terms of ripple, attenuation, and this difference between the pass band and stop band edges was constant, I knew that would converge on 23. Now the optimal number for this might be a little more, a little less. We'll hit optimize and find out. 21, so it was a little less. So something to draw from that is that the optimal number of taps is nearly identical between a high pass and low pass filter with the same band edges. So next let's go to a bandpass filter. I'm going to change some of the specifications around here a little bit. I'm going to have 0.4 kilohertz for my upper passband upper frequency. I'm going to put the bandpass center in the exact center of that. We can't compare this directly to what we had before, because I changed around some of the parameters, but to give you an idea, we still had the 60 dB of attenuation specified for the stop band. We've got two stop bands now because this is a band pass filter, meaning it passes this band in the center based on the center frequency. We've got 1 dB of ripple here in the center of the pass band. We've got these roll-off areas between the pass band and the stop band. And you can see that we exceeded our design requirements here on the edges of the stop band. Next, I'm going to convert our example from a bandpass to a bandstop filter. So we hit the bandstop button. Again, these prompts were changed automatically. We do optimize. And we came up with 23 taps for our bandstop filter. So this is analogous to what we had before. We have an attenuation of 60 dB here in this bandstop, which is centered on 0.25 kilohertz, which is 250 hertz. We've got band edges at 0.1 kilohertz and 0.4 kilohertz. And we ended up with 23 taps instead of 22 taps. Our next design type has multiple stop bands and multiple pass bands. Let's go through the design specifications of this filter. We've got 4 bands, 2 stop bands, 2 pass bands. The first stop band has an attenuation of 90 dB. That's followed by the first pass band that has a ripple of 3 dB. Our second stop band has an attenuation of 60 dB. And our second pass band has a ripple of 1 dB. Here's a close-up of the frequency response. We've got this stop band at the low end, our first pass band somewhere in the middle, a very narrow stop band towards the high side. Then we've got this second pass band at the very top of the frequency range. You'll notice that each of these not only have their own band edges, but they also have their own attenuation. In the case of the stop band here, this is 90 dB of attenuation. This one's 60. We have, let's zoom in on that. So we have a ripple allowance here of 3 dB. And in this top pass band we have a ripple allowance of 1 dB. So that illustrates the point that with the Parks-McClellan algorithm you can essentially have as many pass bands and stop bands as you want, each with their own separate specifications, and the only limitation is that each band edge, this transition area from one pass band or stop band to another, involves more taps. So you'll see on this one, compared to our other examples, we've got 95 taps versus we were in the 23 range I think on the other ones. And that's as simple as the fact that this has more bands. So that's another thing that the Parks-McClellan algorithm can do that other design types can't. Generally is allow you to have separate bands, each with their own specifications. Our next example is a Hilbert transform filter. The purpose of a Hilbert transform filter is to phase shift all frequencies within a pass band by 90 degrees, and it's used in some applications to create a complex signal out of a real signal. So the original becomes the real part of the signal, and the part that's run through the Hilbert transform filter becomes the imaginary part. One thing to bear in mind with this type of design is you can't have a phase shift of 90 degrees at 0 hertz. So a Hilbert transform filter always needs to exclude some area near 0 hertz, including 0 hertz. So this one has been pre-designed It's got a stop band of 80 dB. This is a different specification editor than you've been seeing on Scopefur. We selected the Hilbert transform option. And one of the things to notice about this is a characteristic of the impulse response is it has this anti-symmetrical nature around the center tap. Typically in a signals course or DSP course, they talk about Hilbert transforms as kind of a mathematical thing to turn real signals into imaginary signals, which you can combine with the original to make a complex signal. Our last Parks-McClellan design type is the differentiator. This isn't commonly used anymore. I've never used it myself, but it provides a slope frequency response which can be used to implement an FM demodulator of the discriminator type. That concludes our tutorial on the Parks-McClellan method for FIR filter design. Hope you've enjoyed it and learned something. If so, please give us a thumbs up and consider subscribing to the DSP Guru channel. You can also find us on the web at dspguru.com.